All right, this is question number 4 from the 2010 Form B AP Calculus AB exam. It's a motion question where they've given us this graph here, the graph of the velocity of a squirrel that's starting on building A and traveling across a straight horizontal wire towards building B. And we've got 18 seconds here. We assume, I guess it's seconds. It doesn't actually say. We got a time period from 0 to 18 that we're looking at this squirrel's motion. And we want to know at what times in this interval from 0 to 18 does the squirrel change directions? Well, it's going to change directions when v of t changes signs. So we'll say something like that. The squirrel changes, let's try that again. Squirrel changes directions when v of t changes signs. And the two places that happens are when this velocity curve goes through the t-axis, so at t equals 9, and t equals 15. And so that's just worth 2 points, actually, 1 for the values and 1 for the explanation that whenever the velocity changes signs. So 2 points there for part A. In part B, we want to know when is the squirrel farthest from the building and how far from building A is the squirrel at that time. So this is kind of like actually a little bit of a combination with a graph FRQ, where you have to kind of find the areas underneath the curve. So the position we know at t equals 0 is going to be 0. Okay? And then by the time we get over here, we've had a positive velocity at t equals 9 for the whole time. So we're pretty far away at that point. And so we could have a maximum here. Right? This is a local max because our velocity went from to the right and then to the left. So we're getting closer after that from 9 to 15. Right? This is going to be a local min. And then we're going to have right here at the end, there's going to be another local max. And we'll say local max of the position for each of these, right? Local min of the position and another local max of the position. And so we really just need to find these areas here to figure out when it's furthest away. So we know that at t equals 0, the position is 0. And we'll call x of t the position. So we'll say x equals 0. And then at t equals 9, x should equal, well, whatever the area of this trapezoid is. Well, that trapezoid has a base of 9 and a base of 5. So 9 plus 5 divided by 2 times the height of that trapezoid, which looks like it is 20. So that's 9 plus 5 is 14, and then times 10, if you do 20 over 2, that'll be 140. And then we know that this local minimum is not going to be a possible max, but we do need to figure out how far it traveled back. So, and we could, maybe we'll just write in here that this is 140. And if we find this area in here, right, in fact, we'll kind of just do that over here, that's another trapezoid that's got a base from 9 to 15, which is going to be 6 units. And then another base that is from 10 to 14 here, that's going to be 4 units. Divide that by 2 and multiply by the height. Well, this time the height is 10. And so we're doing 6 plus 4 is 10, divided by 2 is 5, and then times 10 is 50. So this is like going backwards 50. And then at the end here, we got another trapezoid, right? And so this one is going to be, it's got a base from 15 to 18, that's 3. And then a base from 16 to 18, that's 2. And you divide that by 2. And we'll multiply by the height of 10. We got 5 times 10 is 50, divided by 2 is 25. So this one is 25. So that tells us then at t equals 15, our position was 140 minus 50, that's 90. And then at t equals 18, our position is going to add 25 more back to that, so that'd be 115. So the time that it is the furthest away is t equals 9, and it's going to be 140 away from the building. So we'll write something like the farthest distance is 140 at t equals 9. And that'll be our answer here for this. And we got 2 points, one for identifying these candidates, right? T equals 0, 9, 15, and 18, or really just noting that 9 and 18 were the real possibilities, and then one for the actual answer. In part C, it asks us for the total distance traveled on the time interval. So total distance traveled is going to be an integral of the absolute value of the velocity from 0 to 18. Well, we already determined that this was 140, this was 50, but to the left, and then this last piece here was 25. So if we're doing the absolute value, it's just going to be 140 plus 50, right? Because this is effectively going up and becoming like a positive when we do the absolute value. And then we'll add another 25 to it. So 140 plus 50 is 190, and 190 plus 25 is 215. And you get 1 point there for the answer of 215. And in part D, it asks us to write expressions for the squirrel's acceleration, velocity, and distance from the building that are valid at 7 to 10. And so we'll start with the acceleration, right? The acceleration is just the derivative of the velocity. And if we're talking about from 7, so right here, to 10, right here, the acceleration should just be the slope of the velocity curve on that interval. So we'll do that up here because it's going to be a quick and easy one. A of t should just equal whatever that slope is. That slope is always the same. So we'll do y2 minus y1. So we can do negative 10 minus 20 divided by 10 minus 7, which is just going to give us, negative 10 minus 20 is negative 30. And divide that by 3 gives you negative 10. So a of t is just equal to negative 10. So you get 1 point there just for finding a of t. And then to find v of t, an expression for v of t, right? V of t is just going to be the equation of that line, right? So v of t, well, we know it has a slope of negative 10. Right, so if it has a slope of negative 10, and we can then find the equation of that line just by doing point slope form. Right, so we'll do y minus 20 equals negative 10 times, not x, we'll do t minus 7. Which is how we would normally do this. We have y minus 20 equals negative 10t plus 70, or y equals negative 10t plus 90. So we'll say v of t equals negative 10t plus 90. Right? We're just using point slope form to find that linear equation. And you got 1 point there for the velocity. Now, lastly, we need to come up with a function that represents the position on that interval. Well, the position is the integral of the velocity, right? We know that. So what we're going to do is we're just going to integrate v of t here, the integral of v of t dt, well, that should be negative 5t squared plus 9dt plus some constant. Well, we can find that constant because we know that at t equals 7, the position of this, and we'll even write this, x of t is equal to this. The position is going to be equal to whatever the area from 0 to 7 was. And so we can do that just the same way we did before by using using a trapezoid here, right? We've got a base of 7 and a base of 5. We divide it by 2 and then multiply by the length of that interval, or not the length of the interval, but by the height, which is 20. So we end up with 12 times 10, which is 120. So we know that at t equals 7, the position is 120. So we can plug that in to find that constant. So we'll end up with negative 5 times 7 squared, which is 49, plus 90 times 7, plus c is equal to 120. And then, well, negative 5 times 49, and that's just negative 245. And then we have plus 630 plus c equals 120. Well, negative 245 plus 630, what does that come out to be? If we looks like that is going to be 385, right? So if we have 385 plus c equals 120, then c is going to be 120 minus 385, which is negative 265. And so our function x of t should be negative 5t squared plus 90t minus 265. And you got 2 points there for getting that position function. And that is the end here of this motion FRQ, which is question number 4 from the 2010 Form B AP Calculus AB exam. All right, this is question number 6 from the 2010 Form B AP Calculus AB exam. It's another motion FRQ. And we've got two particles moving along the x-axis. And we're given the positions of each of these particles. Particle P has a position of 2 cosine pi over 4t, and particle R has r of t equal to t cubed minus 6t squared plus 9t plus 3. Part A just asks us on 0 to 6, when is particle R moving to the right? Well, if its position is this cubic, r of t, it's going to move to the right when its velocity is positive, which means we need to find r prime of t. So r prime of t is just going to be 3t squared minus 12t plus 9, right? Just using the power rule to take that derivative. We should be able to factor out a 3 from all of that, making this a little easier to look at here. And we'll then factor it again into t minus 1 and t minus 3. And in order to figure out when this is equal to 0, we just use the zero product property and say, well, t equals 1 and t equals 3 is what makes this equal to 0. And we'll make a little sign chart here. I think it's easy to make a sign chart to see if the velocities are positive or negative. So if I plug in something between 0 and 1, like a half, both t minus 1 and t minus 3 are negative. So we end up with 3 times a negative, which is a positive, meaning the particle is moving to the right. And then if we plug in something between 1 and 3, like 2, t minus 1 is positive, but t minus 3 is negative. So we have a positive times a negative there, which gives us a negative, and we're moving to the left. But for things between 3 and 6, like 4 or 5, everything in this r prime is positive, and so we're moving back to the right. And so we'll say r prime of t is greater than 0 for, and then we'll say 0 to 1 and 3 to 6. So r is moving to the right. On those intervals. And they gave you 2 points for this, one for correctly finding r prime and one for the answer with the reason. For part B, it wants us to find all times t when the two particles travel in opposite directions. So we already know which direction r is moving, right? We'll say r, we'll put this off to the side, r is moving right, just so we have it, on 0 to 1 and from 3 to 6, and r is moving to the left on 1 to 3. So we'll make a little note of that, just so we've kind of got that off to the side while we work on particle p. So to determine the direction of particle p, we need its derivative, p prime of t, and the derivative of 2 cosine pi over 4t, well, the derivative of cosine is negative sine. So we're still going to have that 2, and we're going to have negative sine pi over 4t, and then times the derivative of the pi over 4t, which is pi over 4. So what we end up with is negative pi over 2 times the sine of pi over 4t. And we want to know, when does this equal 0? Well, it equals 0 whenever the angle, in this case pi over 4t, is equal to 0 plus pi n. Right? If sine equals 0 at 0 and pi and 2 pi and 3 pi, negative pi and negative 2 pi, right? 0 plus pi times any integer. And so we'll just solve this now by multiplying by 4 and dividing by pi. So we're going to get t is equal to, if I multiply by 4, we're going to just get 0 plus 4 pi n. And if we divide by pi, we're just going to get 0 plus 4n. Well, the only values of n that put us on the interval 0 to 6 here will be n equals 0, gives us t equals 0, and n equals 1 will give us t equals 4. So that's when this particle potentially changes signs. So we'll put on 0, 4, and 6 onto a sign chart, 6 because that's the end of our interval. And if we test something in here like, let's say, 2, right? If I plug in 2 to my derivative, I get the sine of pi over 2, which we know the sine of pi over 2 is positive, but then we multiply it by a negative pi over 2, so that becomes negative and we're moving to the left. And if I put in something like 5, we get the sine of 5 pi over 4, which is negative, but then we multiply by another negative, giving us positive, and we're moving to the right. So now we just need to do a little bit of a comparison here, right? We know that p is moving to the left on 0 to 4. Well, if we look over here, r is moving to the right on 0 to 1. So let's see. We're going to have opposite directions. First of all, on 0 to 1, because particle r is moving to the right and particle p is moving to the left. And then again, it looks like from 3 to 4, particle p is moving left, but particle r is moving to the right. So there's another time. And then when particle p is moving to the right on 4 to 6, it looks like r is still moving to the right on 4 to 6. So it looks like those are the only 2 time periods when they're moving opposite directions. And so that is our final answer here. And we might want to write out that p moves left on 0 to 4 because p prime is negative. And we could also write p moves right on 4 to 6 because P prime is positive. So now we've kind of got it all written out. We've got 3 points here for this. 1 point for just getting P prime correctly. 1 point for analyzing the signs of P here. And so that's why it's good to write these statements out, because they don't want to just see a sign chart. They want to see the analysis of the sign chart. And then 1 point for the final answer. For part C, it wants us to find the acceleration of particle P at t equals 3. So that means we need to find the derivative of P prime, or P double prime. Right, so P double prime of t. Well, P prime we already had, right? P prime, we'll write it over here just so since we don't have it on this page, was negative pi over 2 sine pi over 4 t. And so if I take the derivative of that, I'm still going to have this negative pi over 2 out in front. And then the derivative of sine is cosine. So cosine pi over 4t. But then we also have to multiply by the derivative of pi over 4 again, or pi over 4t, which is pi over 4. And so we end up with negative, it looks like negative pi squared, negative pi squared over 8 times the cosine of pi over 4t. And if we evaluate this at 3, we get negative pi squared over 8 times the cosine of 3 pi over 4. Now we don't actually, we do actually have to find the acceleration there. I was going to say we can just use the sign of it to determine if the particle is speeding up or slowing down, but it asks us to find the acceleration at t equals 3. So we need to know that the cosine of 3 pi over 4 is negative root 2 over 2. So we've got negative pi squared over 8 times negative root 2 over 2. Well, the negatives will cancel, and we end up with pi squared root 2 over 16, which is a good answer there. And we know that that's greater than 0, which is important because we knew that P prime of 3, if we look back at our chart, P prime of 3 was negative over here, right? So P prime of 3 was less than 0, whereas P double prime of 3 was greater than 0. And if the sign of the velocity and the acceleration are opposites, then the particle is slowing down. So we'll say P is slowing down at t equals 3 because P prime of 3 and P double prime of 3 have, make sure that actually looks like a 3, they have opposite signs. And that's the key phrase you want to write, that they have opposite signs, therefore slowing down. Oh, and 2 points for that. We'll go back to that for a second. 1 point for finding this value, and 1 point for the correct answer of slowing down with the appropriate reason. All right, and in part D, we're asked to write, but not evaluate, the expression for the average distance between the two particles on the interval from 1 to 3. Well, the distance between the two particles should just be the positions minus each other. But since we're not always talking about one of them being to the left or to the right necessarily, we can just say the distance between them is the absolute value of P of t minus R of t. Right? That'll be the distance between them. And if we want the average of that distance, right, well, then we just need to do an integral from 1 to 3, since that's the interval we're talking about, with a dt out here, with a 1 over 3 minus 1 in front. This is just the mean value theorem for integrals, right? 1 over b minus a times the integral from a to b of the function. And the function we wanted was a function that represents the distance between the two particles, which is just their positions minus each other. absent of the sign, so we take the absolute value, right? It doesn't matter if P is to the left of R or R is to the left of P, right? The distance between them is always the absolute value of the difference between their positions. And so 3 minus 1, you don't necessarily need to do this, but 3 minus 1, of course, is 2. And so we end up with this as our final answer, and they gave you 2 points for that. And that is the end of question number 6 here. It's a motion question from the 2010 Form B AP Calculus AB exam. All right, this is question number 1 from the 2011 AP Calculus AB exam. It's a motion question. It's a calculator question. And we're given a particle moving along the x-axis on the interval from 0 to 6, where t is, t is our variable here. And we're given that its position, x of t, is not actually given to us, but we do have the velocity and the acceleration, v of t and a of t. And so the first thing it asks us is the speed of the particle increasing or decreasing at 5.5? Well, we've learned that speed is increasing when the velocity and the acceleration have the same sign, whether they're both positive or both negative. Or speed is decreasing if they have opposite signs. So all we really have to do here is just evaluate v of 5.5 and a of 5.5 and see if they're positive or negative, compare the signs of them. Conveniently, we've got a calculator for this problem. So we're just going to evaluate both functions at 5.5. So v of t was 2 times the sine of e to the t over 4. So I like to use the alpha and then the x button right next to it. And then we'll do 5.5 over 4 here, since we're trying to evaluate this at 5.5. We'll close our parentheses on our sign, and then it had a plus 1. So we get negative 0.453 if we round it. So put that in here, negative 0.453, which we'll note is less than 0. And then we'll do the same with our acceleration function. It was 1/2 of e to the t over 4, so I'll just write 0.5 of e to the, and again, it was t over 4, so I'm going to use that same fraction, 5.5 over 4. And then it was times the cosine of e to the t over 4, so e to the 5.5 over 4. And I'll close my cosine there, parenthesis, and we get negative 1.359. And we'll note that that's also negative. And since they both have the same sign, we can say the speed is increasing at t equals 5.5 because v of 5.5 and a of 5.5 have the same sign. And that's the exact justification that you need. They gave you 2 points for the conclusion with the appropriate reason. You need to have the right conclusion and the right reason there to get the points. In part B here, it asks us to find the average velocity of the particle on the time period. Well, average velocity just means do the mean value theorem for the velocity. So 1 over 6 minus 0 times the integral from 0 to 6 of the velocity function, right? 1 over b minus a times the integral from a to b of v of t. And you get 1 point just for setting this up correctly. And you're going to get 1 point for just putting this into your calculator and getting an answer. So we'll do that. We'll put our fraction out in front, 1 over 6. Again, I'm just using alpha and then the x button to get that nice little fraction. If your calculator has that functionality, I recommend using it. And then to put our integral, we're going to hit math. And we're going to go down to option number 9, FNINT. And then that'll just give us our integral. We'll put in the limits from 0 to 6 here. And our function for velocity, again, was 2 times the sine of e to the t over 4. So we got e to the, we'll use x So I'm going to put x over 4, close my parenthesis there on the sign, and then add my 1, because there was a plus 1 after it. And we'll throw our dx out there, and it looks like we get 1.949. And so that is our answer there. And you got one more point for that value. In part C, it wants us to find the total distance traveled by this particle from t equals 0 to t equals 6. Well, total distance traveled is always equal to the integral on that time interval of the absolute value of the velocity, right? We get total distance traveled from an integral of speed, and speed is the absolute value of velocity. So we're just going to put that into our calculator now, and you do get 1 point just for having the correct setup. And then we'll get another point for the correct answer. So again, we're going to just do math, and we're going to do option 9, and you can just hit the 9. You don't have to scroll down. We're going to integrate from 0 to 6, and then you need to know how to do absolute value on your graphing calculator. So you'll hit math. You'll go over to the second column, and it's just option number 1, ABS. And then we're just going to put that same function in there, 2 times the sine of e to the x over 4. Close that parenthesis, and then our plus 1. And then, of course, your dx out in the front, or out of the end. And after a second there, it gives us 12.573. And, of course, we'll get 1 point for that. So there's 6 of the 9 points already. And then we're going to look at part D. It says, for t equals 0 to 6, the particle changes direction exactly once. Find the position of the particle at that time. Well, we need to figure out when it changes direction. And so the only time something can change directions is when v of t is equal to 0. So that's our first step, is to set v of t equal to 0. They actually give you a point just for even beginning to consider that. We're going to go into our graphing calculator. This time we're going to hit y equals so we can actually graph the function. And again, v of t is just 2 times the sine, same function as every other time. So we'll just type that all in, exactly the same as every other time. And we're talking about the interval from 0 to 6. And I like to just be careful and only graph it on that interval. So I'm going to hit window up in the top left there. Change my x minimum to 0 and my x maximum to 6. And then when I hit graph, it's just only going to show me what's going on with the function on the interval I care about. Well, I want the one time when it changes direction. So my velocity goes from positive to negative. Looks like over there around 5. We'll find the exact, or at least a very close approximation to the exact value by hitting second. And then trace, which gives us, the calculate window. We'll choose option number 2 for 0, because that's what we're looking for, is the 0 of this function. And we'll scroll over a ways till we're pretty close to that intercept. Then we'll hit enter while we're still on the left of it. And then we'll go to the right of it and hit enter. And then we'll hit enter again where it says guess. And it'll tell us that that happens at 5.1955223. And so we will say this is true when t is 5.1, write the 1.1955223. And so that's the time that we're interested in finding the position at. Well, to find the position, and I'm going to call this, I'm just going to call this capital A, so I don't have to keep writing 5.1955223 over and over again. We want to find the position at A. And we know the position at 0 is 2. And if we were to do the integral of the velocity from 0 to A, that should tell me the displacement on that interval. In other words, it should tell me the difference between x of A and x of 0. And so if I wanted x of A, it should just equal, I can just add this x of 0 over to the other side. It should equal x of 0 plus the integral from 0 to A of v of t dt. And they gave you 1 point here just for using this integral. And then, well, now we can just find out what that is. So it's going to be, we're just going to do on our graphing calculator, we'll go out of here. Before we actually go out of here, let's note that we have put our velocity function in as y1 already in here. So when I go out hitting second quit, and I need to put in this x of 0, or 2, plus this integral, I'm going to hit math, and I'm going to hit option number 9. And my integral was from 0 to that a value that I had, so 0 to 5.1955223 of the velocity function. Well, I don't want to type it again. I've typed it so many times already. I can just hit the VARS button next to clear, go over to YVARS, choose option number 1 for function, and then pick my y1 function because it is the velocity function. And we'll just put our dx at the end. Let our calculator calculate that integral. Looks like when we round it, it's 14.135. And so that will be our position of that particle at that time. And that is our last point here for part D. And that's the end of this motion FRQ number 1 from the 2011 AP Calculus AB exam. All right, this is question number 5 from the 2011 Form B AP Calculus AB test. It's a motion question. We got this guy Ben who's riding his unicycle back and forth along a straight east-west track. And it tells us that B is a twice differentiable function. And we're given his position on the track, measured in meters from the western end. And then we're also given his velocity, v of t, in meters per second. And it asks us to use the data in the table here to approximate his acceleration at t equals 5. Well, we can approximate the acceleration at 5 just by doing an average rate of change of his velocity on that interval. So, from 0 to 10 will be the one that makes the most sense if we're trying to find it at 5. So we'll do the velocity at 10 minus the velocity at 0 divided by 10 minus 0. That gives us 0.3 divided by 10, or 0.03. It says to indicate units of measure. So we were in meters per second, but we are essentially taking a derivative with respect to time again. So it's going to be not meters per second, but meters per second squared. And they'll give you 1 point there for the correct answer with the appropriate units in part A. In part B, it wants us to interpret the meaning of the integral from 0 to 60 of the absolute value of the velocity in the context of this problem. And then we're going to approximate it using the left Riemann sum. So first off, we know that the absolute value of velocity is speed. And if we integrate speed, then we get a total distance traveled. So we're going to say that the integral from 0 to 60 of the absolute value of v of t dt is the total distance. That's the key word there, the total distance. And then just kind of fill in the right stuff here. The total distance Ben rode his unicycle in meters, because it does say using appropriate units, in meters, from t equals 0 to t equals 60 seconds. And just for the meaning of that integral, then we're going to get 1 point. And then we're going to do the left Riemann sum to approximate this value. So the left Riemann sum with 3 subintervals, we'll do 0 to 10, 10 to 40, and 40 to 60, because that's our only option. We're looking for the total distance, so it's an integral of the velocity, so we're going to be putting in our velocity values here. So the first interval is from 0 to 10. That's a width of 10. And then the velocity at 0 is 2. And then we'll add to that the 30-second interval from 10 to 40 times the left side of that interval, which is 2.3. And then we'll add to that 60 to 40 is 20. And then, of course, we want the left end of that interval. So we just have 10 times 2 plus 30 times 2.3 plus 20 times 2.5, which comes out to be, let's see here, that's 20 plus 69 plus 50, looks like that's 139 meters. And you got a point there for the approximation as well. In part C, it says for t equals 40 to t equals 60, is there a time when his velocity is 2 meters per second? And so we have a couple of different options here. One would be to just look at the interval from 40 to 60, knowing that the velocity is continuous, to see if one of the values is more than 2 and one of the values is less than 2. But when we look at that, and that would be the intermediate value theorem. When we look at that, it looks like his velocity was always above 2 on that interval, just based on the data in the chart. But that doesn't just guarantee that his velocity never dipped below 2. So the other option is to use the mean value theorem with 9 and 49. And the mean value theorem says that if the function is continuous, which b is continuous, we know it's continuous because we knew that b was twice differentiable. So a function is, if a function is differentiable, that implies that it is continuous. So b is continuous on 40 to 60 and differentiable on 40 to 60. And again, this one's an open interval, right? Because that's how the mean value theorem works. And we know it's continuous. We can say this is because it is differentiable. And then we can look for the average rate of change on that interval. So we can say, and the average rate of change, right, is just going to be 49 minus 9 over 60 minus 40. Well, that equals 40 over 20, which is just 2. So we can then say, since the average rate of change on the interval from 40 to 60 equals 2, mean value theorem guarantees that b prime, and we could say b prime of, it doesn't matter, b prime of c is equal to 2, which is v of c, on the interval 40 to 60. That's what the mean value theorem says. And so you got 1 point for just doing this little difference quotient and 1 point for the answer of, yeah, it does. And here's all the reason. It's the mean value theorem, and you have to state that it's continuous and differentiable and all of that good stuff. So 2 points there for part C. And in part D here, we've got a light that is directly above the western end of the track, which is where Ben started. And he rides so that the distance between him and the light satisfies this equation, L of t squared equals 12 squared plus b of t squared. And we want to know at what rate is the distance between Ben and the light changing at t equals 40. Well, this is just a related rates question here. And so we'll just take the derivative of this, right? We're going to get, and it's all in terms of t. So when we take the derivative with respect to t, we're just getting, we don't have to write these like dl dt's. We kind of have those built in. The derivative of a function squared is 2 times the function times the derivative of the function. And so 2 times L of t times L prime of t. and then the derivative of 12 squared, well, 12 squared is 144, and 144 is just a number, so that can just be eliminated. Derivative of a constant is 0, and then we have 2 times b of t times b prime of t, just like we did with the other one. And we can, of course, cancel out the 2's just to make our lives a little bit easier. And now we just need to see what's going on here at 40, right? So the distance, which is L of t, we're looking for the rate of change of L. So that's L prime of 40 that we're looking for. So we want L prime of 40. Well, that should equal B of 40 times B prime of 40, all divided by L of 40. And B of 40 we can find in the chart. That's 9. B prime of 40 we can also find in the chart, because remember that B of t is B prime. So we have 9 times 2.5. And then in the denominator we have this L of 40. Well, L of 40, that's going to come from this. So we know that L is equal to the square root of 144 plus B squared. So L of 40 will just be the square root of 144 plus B of 40 squared. Well, B of 40 is 9, and 9 squared is 81. Right? And so now we'll just evaluate this. Let's see here. 144 and 81 is going to be 225. So that's going to give us a 15 here. So we have 9 times 2.5 over 15. 9 over 15. That'll both divide by 3. So we're going to get 3/5 there. So really this is 3/5 times 5/2, because that's what 2.5 is. 5's will cancel, and you get 3/2. It doesn't necessarily ask for units here, but it's in meters per second. And they gave you 3 points here for this. 1 for having the derivatives correct, 1 for knowing that B prime was equal to V. So basically 1 for putting in 2.5 there, and 1 for the final answer. And then that's only 8 points here, but they gave you a 9th point if you had the correct units in either A or B, right? So you didn't have to have it in both of them, but as long as you had the right units in either A or B, then you got the 9th point. And that's the end here of question number 5, this motion question from the 2011 Form B AP Calculus AB exam. All right, this is question number 6 from the 2012 AP Calculus AB exam. It's a motion FRQ, and we've got a particle moving along the x-axis from t equals 0 to 12, and we're given its velocity function, cosine of pi over 6 times t. We're also given an initial position that at t equals 0, the particle is at a position of x equals -2. First question it asks us is, when is the particle moving to the left? Well, in order to figure out when a particle moves to the left or to the right, you need to see when its velocity is negative and when it's positive. And the only time it can change from positive to negative is when that velocity function, in this case cosine of pi over 6t, is equal to 0. So we're looking for all of the solutions to that on the interval 0 to 12, so that we can then test and see when it's moving left and when it's moving right. Well, we know that cosine is equal to 0 at pi over 2 and 3 pi over 2 and 5 pi over 2 and negative pi over 2 and so on. Right? Whenever the angle, in our case the angle is pi over 6t, is equal to pi over 2 plus any pi n, right? Because that satisfies negative 3 pi over 2 when n is -2, or negative pi over 2 when n is -1, or pi over 2 when n is 0, and so on, right? 3 pi over 2 when n is 1, and everything along all of those solutions to this equation. So now we just need to solve this little bit for t. So we'll first, we can multiply by 6, and we can also divide by pi. So if I multiply by 6 and divide by pi, the pi's are going to go away, and we're going to end up with 3 plus 6n. And so we're just looking for the solutions to that for integer values of n that are on 0 to 12. Well, when n is 0, we get t equals 3, so that works. If n is negative, that's not going to work because we'll have negative values. When n is 1, we get 3 plus 6, which is 9. But when n is 2, we're going to be outside of the interval from 0 to 12. So we have two possibilities here. T equals 3 and t equals 9 are places when it changes from left to right potentially. So now we'll just make a little sign chart here for the velocity using 0, 3, 9, and 12. And we'll plug in some values and see when it's positive and when it is negative. So if we plug in something like 1 in, we get the cosine of pi over 6. Right? Well, the cosine of pi over 6 we know is positive, right? Because that's a first quadrant angle. But if we plug in something like 6, we get the cosine of pi. And we know the cosine of pi is -1, so it's negative on this interval. And something larger than 9 but less than 12, let's say like 10, right? That's going to be the cosine of 10 pi over 6 or 5 pi over 3. That's in the fourth quadrant where we know cosine is positive. And so the question is, when is it moving to the left? Well, it's moving to the left when its velocity is negative. So we'll say that. We'll write exactly that. It moves left if v of t is less than 0, which is true on the interval from 3 to 9. And so we're going to get 2 points there, one for just considering when this is equal to 0 and one for the actual answer. For part B here, it asks us to write, but not evaluate, an integral expression that gives the total distance traveled by this particle from 0 to 6. Well, total distance traveled is always an integral of speed. And we know speed is absolute value of velocity. So we just want the integral of from 0 to 6 of the absolute value of v of t dt. That's literally all you have to do. That's worth 1 point for part B. In part C, it asks us to find the acceleration of the particle at time t. So find a function that represents that. So that's easy enough. A of t is equal to v prime of t. Well, v prime of t is just the derivative of the cosine of pi over 6t. That requires the chain rule. Right? So it's the derivative of cosine, which is negative sine of pi over 6t, times the derivative of pi over 6t, which is pi over 6. And so our acceleration function is negative pi over 6 sine pi over 6t. You get 1 point for that. Then the second part says, is the speed of the particle increasing, decreasing, or neither at t equals 4? Well, speed increases when velocity and acceleration have the same sign, and it decreases when they have opposite signs. So we'll just go ahead and see what the velocity was at 4. So we knew that the velocity at 4 was less than 0. We don't need to actually find the value, but we know it's less than 0 because we figured that out back in part A here, right? If we look back, right, it was moving to the left. The velocity was negative on 3 to 9. So we know v of 4 is negative. And then we can find a of 4. A of 4 is negative pi over 6 times the sine of 4 pi over 6, or 2 pi over 3. Well, the sine of 2 pi over 3, right, is root 3 over 2. So we end up with negative pi root 3 over 6 times 2, which is 12. So negative pi root 3 over 12, which is clearly negative. Also, if the signs are both negative for velocity and acceleration at that time, the particle is got its speed increasing. So we will say the speed is increasing at t equals 4 because, and then we'll say v of 4 and a of 4 have the same sign. And you can say they're both negative if you want. That's acceptable too. But just saying that they have the same sign is perfectly sufficient. You got 2 more points for the correct conclusion with reasoning. And our last part here is part D here. Find the position of the particle at t equals 4. We haven't done anything with the position yet, other than we know that if we integrate velocity, we get displacement, right? So the integral of v of t dt from our initial condition of 0 to what we're looking for should be the displacement of the particle from 0 to 4. In other words, it should be the position of the particle at 4. We'll say x of 4 minus x of 0. And if we want x of 4, well, x of 4 should just be our initial position, x of 0, added to this side. So plus the integral from 0 to 4 of v of t dt. Well, x of 0 was negative 2, so we have negative 2 plus the integral of v of t. And to integrate, we'll do this off to the side, to integrate cosine pi over 6 times t, it's a u sub, right? You're going to let u equal pi over 6, and du, not pi over 6, pi over 6t, and du will be pi over 6 dt. So really what you want to do is you're going to want to put in a pi over 6 here inside your integral, and a 6 over pi outside your integral. And so that gives you now 6 over pi integral cosine u du. And of course the 6 over pi can be inside, so I don't have to worry about any weird stuff going on there. The integral of the cosine is sine, so we end up with 6 over pi sine of u, and u of course was pi over 6t. So there's our integral, and we just need to evaluate it from 0 to 4. So now we have negative 2 plus 6 over pi times the sine of 2 pi over 3. Well, the sine of 2 pi over 3 is root 3 over 2. And then minus 6 over pi times the sine of 0. We know the sine of 0 is 0, so I'll just put a 0 there. So now we end up with our final answer of negative 2 plus, and we can cancel the 6 over the 2 as a 3 in the numerator. So we have negative 2 plus 3 root 3 over pi. And that should be our final answer. They gave you 3 points here for part D. 1 point for the correct antiderivative here. They gave you 1 point for remembering to use the initial condition, and 1 point for the final answer. And that is the end of this motion FRQ, which was question number 6 from the 2012 AP Calculus AB exam. All right, this is question number 2 from the 2013 AP Calculus AB exam. It's a motion question. We've got a particle moving along a straight line, and from 0 to 5, we have its velocity function. And they're calling the position function s of t. We know that the initial position, so the position at t equals 0, is 10. So the first question it asks is to find all values of t on the interval 2 to 4 for which the speed of the particle is 2. Well, we know that speed is equal to the absolute value of velocity. So what we're looking for is when is the absolute value of v of t equal to 2 on the interval from 2 to 4. That's all we care about, is from 2 to 4. And so since this is a calculator problem, we can just conveniently go in to our graphing calculator, hit y equals. We can graph the absolute value of v of t. So to get absolute value, you hit math, you go over to the second column, and then you choose option number 1. And then we're going to just type in our v of t function, which is negative 2 plus, and then we've got in parentheses here, it's t squared plus 3t, but we'll have to do x squared plus 3x. The variables don't really matter here. So x squared plus 3x to the power of 6/5. So I'm going to make a little fraction by hitting alpha and then the x button next to it. 6/5. And then after that, we've got minus t cubed, so minus x to the third. And so we want to graph this, but we only want to look at it from t equals 2 to t equals 4. So I'm going to hit the window button up there near the top left. I'm going to change my x minimum to 2 and my x maximum to 4. And then I'm going to graph it. And we will realize that what we needed to do was see when this is equal to 2, not just when it's equal to 0. So what we needed to do actually was graph also the line y equals 2 here and see where they intersect. Another option would be just to subtract 2 from the original function. I'll just graph y equals 2. Since most of the other ones we've always subtracted and found the x-intercepts, this time we'll do the intersection points. So we can see that 2, y equals 2, intersects that absolute value of the velocity function twice. We're going to hit second trace. We'll go down to option number 5, which is intersect. It says first curve. Just kind of go close to the intersection point on that first curve and hit enter. And then just go maybe a little past the intersection point on the second curve and hit enter. And you get 3.127629 or 3.128 when we round. So we've got at t equals 3.128. And we're going to have a second value here. And our second value, we'll hit second trace, option 5 again for intersect. And now we want to go over closer to that second intersection point. Hit enter, go a little past it, hit enter a third time, and we get 3.473402, or just 3.473 when we round. And they gave us 2 points here, one for the setup and one for getting both of the answers correct. In part B, it asks us to write an expression involving an integral that gives the position s of t. And we want to use that expression to find the position of the particle at t equals 5. So we want the position. And so if we integrate velocity, we do get position. But we have to take into account that like a definite integral of the velocity gives you a displacement. And so if we start at 10, when we get that displacement, we have to take that 10 into account. So our position at any time after t equals 0 should be wherever we were at t equals 0, which is 10, plus an integral from 0 to whatever t value we are interested in of the velocity function. So that's 1 point, just finding this function. And then to get the second point, we want to use it to find the position at 5. So we just want s of 5, which is 10 plus the integral from 0 to 5 of v. Well, our calculator will allow us to do that. So we'll just go into our calculator, and we're going to use a little trick here to make our lives a little easier. We're going to go back to y equals. We don't really need these absolute values anymore, so I'm going to delete that. And I don't think I'm going to need this y equals 2 again. So now I just have my original v function in there as y sub 1. And so now I'm just going to hit second quit and go back to my, my original screen here and type in what I need. I need 10 plus the integral, so math, and option number 9, the integral from 0 to 5 of that function that I have typed in as y sub 1. Well, since I already have that function typed in as y sub 1, I can use the variables button, VARS here, just to the left of clear. We'll go over to the second column, y variables, and under number 1, function, we're just going to use y1. And then we don't have to retype that whole function and potentially have like a little error in typing it in. We'll just hit enter there, and we end up with negative 9.207. And that will be the position of our particle at t equals 5. And that's the second point of part B, or the second point there. In part C, it wants us to find all times t in the interval 0 to 5 in which the particle changes directions. Well, in order to figure out when it changes directions, we have to see when its velocity is 0, and actually also when the velocity changes signs. It can only change signs on a continuous function, which we have, when the velocity is equal to 0. So let's set v of t equal to 0, which now that we've just got on our graphing calculator the function v of t, that's really convenient. We'll just graph v of t and see when it's equal to 0. Now this time we're talking about the interval 0 to 5. So make sure that you hit window. And now change, because before we were doing 2 to 4, now we want to change that to 0 to 5. Now when we graph it, we'll be able to see that there are two places where it crosses through that x-axis on our graph, or the t-axis if we were looking at this velocity on a t v graph. So we'll hit second, trace. Option 2 this time for 0. And we'll do this one on the left first. So we're going to scroll all the way over here. You have to go to the left of the intercept because it says left bound. Okay, we can see we're now to the left. We'll hit enter. When it says right bound, scroll to the right of the intercept, hit enter. It'll say guess, hit enter one more time, and we get 0.536. So we'll first say this is true at t equals 0.536, and we'll even make the note, so that's one place, because the velocity goes from, if we look at the graph, it looked like that velocity went from negative to positive. Okay? So the velocity goes from negative to positive. And then we'll find the other value. So we'll hit second, trace. Again, option 2 for 0. And now we'll scroll way back over here. All right, now we're just to the left of that intercept. Hit enter. It says right bound, go just to the right. Hit enter a third time, and we get 3.318 when we round that. And so we'll say, and t equals 3.318 because v of t goes from, this time, positive to negative, right? And so for the first one, when it went from negative to positive, right, the velocity was going from negative to positive means the particle was going from left and then it moved to going right. And now the second one, since it was starting out positive velocity, is moving to the right, and then it switched and started moving to the left. And you got 3 points here. One just for considering when is v of t equal to 0, and one is for having, or the other two are for having both of these answers with the correct justification. And here in part D, we want to know, is the speed of the particle increasing or decreasing at t equals 4? And so speed increases when velocity and acceleration have the same sign, and speed decreases when they have opposite signs. So at t equals 4, we already know that the velocity, if we look back at our graph, at t equals 4, right, which is past our, where we can even see our function, it's, we're at 3.317, so even further over here at 4, the velocity is clearly negative. We don't need an actual value, but we can say we know that v of 4 is less than 0, and we can say that the acceleration, which is the derivative of the velocity, right? We can find a of 4 and see if they have the same signs. And we can just use our graphing calculator once again to find the value of a of 4. So, and we can we can just go right out of here if we want here. We'll hit math. We'll go down to option number 8 in deriv. We're looking for the derivative with respect to x of that velocity function, which again, remember, we can hit VARS, go over to the second column, option 1, and then option 1 again, just pops that function in there. And we're looking for it at 4, which is negative 22.296 if we round. And so we note that that's less than 0 also. So we can say that the speed of the particle is increasing at t equals 4 because both velocity and acceleration have the same acceleration. If I could spell correctly, acceleration, have the same sign at that time. That they're both negative. You don't need to indicate that they're both negative. We did up here, we said we need to indicate it somewhere, but it doesn't have to necessarily be right there. We can just say that they have the same sign, and that's fully sufficient. You get 2 points there for the correct conclusion with the appropriate reason. And that is the end here of this motion FRQ as question number 2 from the 2013 AP Calculus AB exam. All right, this is question number 4 from the 2014 AP Calculus AB exam. It's a motion problem. We've got a train that's going back and forth on an east-west section of railroad track. We're given a chart with its velocity, v sub a of t, measured in meters per minute. We know that that's a differentiable function, and we've got values at 0, 2, 5, 8, and 12 of the velocity. We want to find the average acceleration. Well, the average acceleration of the train on 2 to 8 ought to be the mean value theorem for the acceleration function of the train. And since we know that the acceleration, we'll call it a sub a, right, since we're using v sub a here, we'll say a sub a of t is v sub a prime of t. Right? So therefore, that means that the average acceleration ought to be 1 over 8 minus 2 times the integral from 2 to 8 of a sub a of t dt. Well, that would be 1/6 of the integral of that a sub a, which is just going to be v sub a of t from 2 to 8, or it's 1/6 of v sub a of 8 minus v sub a of 2. Well, from the chart, we can find v sub a of 8 and v sub a of 2. So we have 1/6 of negative 120 minus 100. Negative 120 minus 100 is negative 220. And so if we divide that by 6, negative 220 over 6 is negative 110 over 3. If you want to put your units, it's meters per minute or meters per minute squared. It doesn't ask for the unit, so it's not really necessary, but you're always welcome to put it. They just gave you 1 point there for getting the correct answer there. That's it for part A. In part B, it asks if the data in the table supports the conclusion that the train's velocity is negative 100 sometime between 5 and 8. And so the answer to this is yes. And the reason is because we know this function is continuous, right? V sub a of t is continuous because it is differentiable, right? It tells us it's differentiable. And so that guarantees us that it is a continuous function. And so we can then use the intermediate value theorem, which just says that if I can find a place where the velocity is less than negative 100 and a place where it's more than negative 100, then it must equal negative 100 on that interval. And since at 5 it's 40, which is more than negative 100, and at 8 it's negative 120, which is less than negative 100, it must equal negative 100 somewhere. So we'll say that v of 5, which is 40, is greater than negative 100, and v of 8 is negative 120, which is less than negative 100. So since it's continuous and it goes from below negative 100, well, it actually goes from above negative 100 to below negative 100, we could say that the intermediate value theorem guarantees that v sub a of t is equal to negative 100 somewhere on the interval from 5 to 8. And that's worth 2 points. 1 point for making this note here that we've got 2 values that are surrounding negative 100, and 1 for the conclusion that uses the intermediate value theorem. And yes, you do need to state the intermediate value theorem for it, to use those words. For part C, it says at t equals 2, the train's position is 300 meters east of origin station, and it's moving to the east. We want to write an expression involving an integral that gives the position of the train in meters from the origin at t equals 12. Then we're going to approximate that with a trapezoidal sum. So first we need the position. So we know that the displacement, right, or basically the distance from where it started, right, should come from an integral of v sub a. So we know that the integral from, and we're talking about from 2 to 12 here, the integral from 2 to 12 of v sub a of t is the displacement on that interval. So that should equal the position. We'll call it, since it's moving east-west, we'll call it, it doesn't give us a letter for it, I don't believe, so we'll just call it x sub a, the position. It's equal to x sub a of 12 minus x sub a of 2, where we know that x sub a prime of t is v sub a of t, right? That's the position function. So that tells us that if we want the position at 12, just add the position at 2 to this integral. So we can say that x sub a of 12 is equal to x sub a of 2 plus the integral from 2 to 12 of v sub a of t dt. And so that's the function that they're asking us to write, or the expression that they're asking us to write that gives it to us. So that's part of our answer here. And then we get 1 point for doing that. And then they want us to approximate that integral using a trapezoidal sum, and then we'll add that initial position to it. So it was 300 meters to the east of the origin, which if it's to the east of the origin, that means that its position is going to be 300 at that time. So we're going to have 300, and then plus the trapezoidal sum. Well, the trapezoidal sum is it's going to look like, you know, the average of the, we're going from 2 to 12, so don't do 0 to 2. The average of the 100 plus the 40, so that'll be 100 plus 40 over 2 times that distance from 2 to 5, which is 3. And we're going to completely run out of room here. Let's just put this on a new page. We've got the 300, and then we've got plus 100 plus 40 over 2 times 3. And then we're going to add to that the next one here, which is going to be 40 plus negative 120 divided by 2. And that one's also going to get multiplied by 3. So we've got 40 minus 120 divided by 2, also times 3. And then we'll add to that the last one here, which is going to be negative 120 plus negative 150, or negative 120 minus 150, divided by 2. And then we'll multiply that one by 4, the distance from 8 to 12. So we've got negative 120 minus 150 over 2 times 4. And that is the setup here for our trapezoidal sum. You know, you have to just do all this arithmetic here. I'm not going to go through all of the arithmetic, but 300 plus all that stuff ends up giving us a value of negative 150. And so we got a point for this, and we got a point for the answer. Now, the wording of the question says approximate the position of the train. And so it would be better, rather than just writing negative 150, we'd want to say it's something like it's 150. Our units were meters here, so 150 meters to the west of the station, right? Because to the west of the station was negative values, and to the right was positive values, or to the east was positive values. All right, and then we've got part D here. We've now got a second train, train B, that's traveling north from the station, and its velocity is this v sub b of t function, and we know that at time t equals 2, that the train is 400 meters north of the station. We want to find the rate at which the distance between them is changing. So what we've got is train A and train B. And so basically we've got a right triangle. Here's origin station. It's a right triangle. And we've got train A moving to the west and train B moving to the right. So we have this distance here that we'll call x sub A, or I guess we called it a capital A before, so we'll do that. And here we've got y, and we'll call it y sub b, whatever that distance is. And this distance in the middle here we'll call z, right? That's the distance between the two. And so we know that z squared is equal to y sub b squared plus x sub a squared, right? Using the Pythagorean theorem. And then we can just take the derivative of this with respect to time, right? This is just a related rates question. So this tells us that 2z dz dt equals 2y sub b dy sub b dt plus 2x sub a dx sub a dt. And of course, the 2's can all just cancel each other out. We're looking for the value of dz dt. So if we just plug everything we've got in here, we don't have a value for z yet. We'll figure that out in a second. We're looking for dz dt. The value of y is just the position of that train at t equals 2, which is 400 meters north. So zy is 400. dy sub b dt is the velocity of that train at 2. So that would just be this function here evaluated at 2. So negative 5 times 2 squared plus 60 times 2 plus 25. Looks like that's negative 5 times 4, which is negative 20. And negative 20 plus 25 is just 5, and then we'll add 120 to that. So we're going to get 125 there. So we've got 400 times 125. And then we've got our x sub a, our position of the first train at t equals 2. And that was given to us in one of the other parts. Looks like it was right here. So its position is 300 meters to the east. So here we've got 300 for x sub a. And then dx sub a dt is the velocity of that first train at 2, which we know is 100. And now we do still need the value of z here. Well, we should be, we have positions of 300 and 400 for x and y respectively, right? 300 squared plus 400 squared equals z squared. We should know that that's just a 3, 4, 5 right triangle, just all multiplied by 100. So z is just going to be 500 here. So we've got 500 dz dt equals 400 times 125 plus 300 times 100. Kind of annoying arithmetic here. If we just divide everything by 100, we got, if we divide both sides by 100, this is now just 4 times 125, which is 500. And this is now just 300 times 1, so just 300. So really, we just end up with 800 divided by 5. We get dz dt is equal to 160 meters per minute. And part D was worth 3 points. 1 point was just for that final answer, and the other 2 points was for correctly differentiating using implicit differentiation. Not 1 point, but 2 points there for correctly doing the implicit differentiation. So 3 points there on part D. And that is the end of this motion FRQ, question number 4 from the 2014 AP Calculus AB exam. All right, this is question number 3 from the 2015 AP Calculus AB exam. It's a motion question. We've got this person, Johanna, who is jogging along a straight path, and we've got a chart of her velocity. And we've got some, selected values of it. T is in minutes and V is in meters per minute. And first thing we want to do is just estimate the value of V prime of 16. The easiest way to do that will just be to find the average rate of change on the smallest interval in our chart surrounding 16. So we'll say it's approximately equal to V of 20 minus V of 12 all over 20 minus 12. And so that's just going to be 240 minus 200 over 8. That'll be 40 over 8, which is just 5. And it doesn't ask for units, but it doesn't hurt to put meters per minute or meters per minute squared. And they just gave you 1 point here for the approximation. And that's it for part A. In part B, it says, using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of V of t dt, and then to approximate it using a right-Riemann sum. So the integral of the absolute value of velocity is an integral of speed. And an integral of speed tells us a total distance traveled. So the integral from 0 to 40 of the absolute value of V of t dt is the total distance that Johanna jogs in meters, because it says using correct units. So in meters for t equals 0 to t equals 40 minutes. And then it wants us to approximate this using a right-Riemann sum using the data in the table. Right? And so the right-Riemann sum, we'll first do 40 minus 24, and we'll write this out. 0 to 40 of the absolute value of V of t dt should be approximately equal to, using our right-Riemann sum, 40 minus 24 is just 16. And I always like to start on the right-hand side when I do the right-Riemann sum, but you don't have to. And then we're going to multiply that by the right-hand value of that interval, which is 150. And then we'll add 24 minus 20, which is 4. And then it's going to be the value at 24, except it's not actually the value at 24, it's the absolute value of that. So that's going to be 220, not negative 220. And then 20 minus 12 is 8. The right hand of that is 240. And then the last one is 12 times 200, because the right hand end of that is 200. And so you just go through and do all the arithmetic. I'm not going to belabor you with me doing the arithmetic. This just comes out to be 7,600 meters. And this was worth 3 points, 1 for the explanation, 1 for the form here, the correct form of the right-Riemann sum, so like all of this stuff, and then 1 for the final answer. In part C, we've got this other person, Bob. Bob's riding his bicycle along the same path, and his velocity is given by this function b of t, t cubed minus 6t squared plus 300. We want to find his acceleration at t equals 5. Well, the acceleration, right, of Bob should just be b prime of 5. And so we can find b prime of t. B prime of t is just 3t squared minus 12t. So we can then evaluate that at 5. 3 times 5 squared minus 12 times 5 just gives us 75 minus 60, or 15. And again, our units here are the same, meters per minute squared, as they were before. It doesn't ask us for units again, so really 15 is sufficient. And we get 2 points here, 1 for using b prime and 1 for actually doing it correctly and getting the right answer. And in part D, it asks us to find Bob's average velocity on this interval from 0 to 10. Well, the average of any function is 1 over b minus a. I don't need to write b. We have a b value. It's 10. 1 over 10 minus 0 times the integral from 0 to 10 of the function that represents his velocity. Well, that was b of t, which was t cubed minus 6t squared plus 300. And so this is the correct setup that we want. And they give you a point for just having the integral there. And then they give you a point for correctly anti-differentiating. So we have 1/10 of t to the 4th over 4 when we integrate the first piece. The next piece becomes minus 2t cubed, and the last piece becomes 3000t. They give you 1 point here for correctly integrating, and then they're going to give you 1 point in the end for having the correct answer. So we end up with here, we have 1/10 of, and we're doing this from 0 to 10. So this is 10 to the 4th. Well, I guess we can write that out. 10 to the 4th power is going to be 10,000 over 4 minus 2 times 10 cubed, so minus 2,000, and then plus 300 times 10, which will be 3,000. And of course, when we plug in 0 to all that, we just get 0. And 10,000 divided by 4 is 2,500. We subtract 2,000 is 500. And we add the 3,000 is 3,500. We divide by 10, gives us 350 meters per minute should be his average velocity. And that is the last point here for part D. And that is the end of question 3 here on the 2015 AP Calc AB exam, this motion problem. All right, this is question number 2 from the 2016 AP Calculus AB exam. This is a motion problem, and we're given a particle that's moving along the x-axis for t values greater than or equal to 0, and we're given its velocity function, 1 plus 2 sine of t squared over 2. We're also given its position is x equals 2 when t is 4. And we now want to know, at t equals 4, is the particle speeding up or slowing down? Well, determining whether the speed is increasing or decreasing has to do with the velocity and the acceleration. So first we just need to find v of 4. And so we've got a calculator for this problem, so we'll just use our graphing calculator to evaluate v of 4. Right? It's going to be 1 plus 2 times the sine of 4 squared, which is 16, divided by 2, which is just going to be 8, right? Because our t was 4 and it was t squared over 2. So that gives us 2.9787164. I'm just going to say it's 2.979. And I'll note the important thing about that is that it's positive. And then I want to find the acceleration. So I'm going to need to find v prime of 4, which is a of 4, and see what that is. And our calculator will do that for us as well. So we're just going to hit map. We'll go down to option number 8 in deriv. We'll do a derivative with respect to x, and we're going to use x instead of t, and we'll do 1 plus 2 times the sine of, and I'm going to hit alpha and the x button next to it just to get a nice little fraction there. It's x squared over 2. And we'll close the sign parenthesis. And we're looking for the derivative of that velocity function when x is 4. So we'll type in a 4 there, and we get negative 1.164. Which is clearly less than 0. And when the velocity and the acceleration have opposite signs, the speed is decreasing. So we'll say the particle is slowing down because v of 4 is greater than 0 and a of 4 is less than 0. And really we want to kind of make the statement that so velocity and acceleration have opposite signs. And that's the key words they're looking for. So you didn't even really need to rewrite that v was greater than 0 at 4 and a was less than 0 at 4, right? Because we already showed that up there. But really what you have to say is that at that time, the velocity and the acceleration have opposite signs, so it's slowing down. And they gave you 2 points, all of it for the correct conclusion with the appropriate reason. In part B, it wants us to find all time intervals, or all times t on this interval, 0 to 3, when the particle changes directions. So a particle can only change directions when its velocity is equal to 0. So we're going to first look for when is v of t equal to 0. So we'll just graph v of t on our graphing calculator. We'll hit y equals. We'll type in our function 1 plus 2 times the sine of x squared over 2. And this was asking for all the times between 0 and 3. So instead of just hitting graph, I'm going to hit window. I'm going to change my x minimum to 0 and my x maximum to 3 so that I'm certain that I only look at the chunk of the graph that they're telling me to look at. And so we can see that the velocity is positive for most of this interval, but it does cross through somewhere between 2 and 3 and become negative. So we need to find that. We're going to hit second and then trace. Option number 2 is 0. We're going to hit that. And then it says left bound, so we're just going to make sure we're to the left of that intercept, and we'll just scroll over till we're pretty close to the x-intercept. Close enough. Hit enter. It'll say right bound. Scroll over till you're to the right. Hit enter. And it says guess, and you'll say enter again, and it'll give you 2.707468. So that's when this velocity is equal to 0. So we'll put that down, 2.707468. And we will say here that the velocity, or the particle, changes directions. So the particle changes directions at t equals 2.707. We can just round it there to 3 decimals if we want, because we'll say v of t goes from positive to negative. We'll just say at this time. And we could have just said it goes from positive to negative at t equals 2.707, therefore it changes directions. And so that's worth 2 points, 1 for the value and 1 for the reasoning that the velocity goes from, I didn't write the word positive, the velocity goes from positive to negative at that time. For part C, it wants us to find the position of the particle at t equals 0. And we're given its position is x equals 2 when t is 4. Well, we know that we should be able to find the displacement of the particle. And we can even do this going backwards. I can say the integral from 4 to 0 of v of t dt should equal the position function, which we'll call x, evaluated at 0 minus x evaluated at 4, the upper limit minus the lower limit, which tells us that the position at 0, x of 0, should just be equal to x of 4 plus the integral from 4 to 0 of v of t dt. And we'll just put that all into our calculator. X of 4 is just 2. So we're just going to do 2 plus this integral. So we'll go out of our graph here. We'll do 2 plus, and then math, option 9. And then our limits are going to be 4 to 0. And instead of retyping the whole function again, since I already have it graphed as my y, and my y equals, I can hit this VARS button next to clear. And over in the second column, y VARS, we can choose option 1 for function and pick our function y1 and just put it in there with our dx. It'll do the integral for us, and we end up with negative 3.815. And you got 3 points here for part C. 1 for having this integral somewhere, 1 for using the initial condition, and 1 for the correct final answer. And here in part D, we're looking for the total distance the particle travels from t equals 0 to t equals 3. Well, total distance traveled is an integral of speed. And speed is the absolute value of velocity. So all we want is an integral from 0 to 3 of the absolute value of v of t dt. And you actually get 1 point just for writing that integral. And you'll get your second point for the actual value, which we'll find on our calculator. So we'll do math, option number 9. Again, you can just hit 9. You don't have to scroll down to it. We're going to integrate from 0 to 3. And then to get the absolute value, you're just going to hit math, go over to the second column and pick option 1. And again, we'll do the same thing we did before. Since our velocity function is already graphed in our graphing calculator, we can just hit VARS, go to the second column, option 1, and then pick y1 again. Now it's inside of our absolute value, just like we want it to be. And our graphing calculator here tells us that the value is 5.301 when we round to 3 decimals. And that will get you the last point for part D, which is the 9th and final point for this motion FRQ number 2 from the 2016 AP Calculus AB exam. Oh, right. This is question number 5 from the 2017 AP Calculus AB exam. It's a motion FRQ, right? We've got 2 particles moving along the x-axis from 0 to 8. Particle P has a position given by x sub p of t. And the velocity of particle Q, the other particle, is given by v sub q of t. And we're also given here an initial position. Particle Q is at 5 when t is 0. And we want to know, first off, for t equals 0 to 8, when is particle P moving to the left? So in order to figure out when a particle is moving to its left or to its right, we need its velocity to be either negative or positive. Moving to the left would be a negative velocity, and moving to the right would be a positive velocity. Well, we don't have the velocity of particle P, so we need to find it. Right? V sub p of t is going to equal x sub p prime of t, which is the natural log of a function. Its derivative is 1 over the function times the derivative of the function, so 2t minus 2. So there's v sub p of t, and we want to know, when is that greater than 0, or not greater than 0, when is that less than 0, right? Because we want to know when is it moving to the left. So we'll say v sub p of t will be less than 0, and we have to figure out the intervals. Well, this thing can change signs, go from positive to negative whenever it's equal to 0, or potentially when it's undefined, but it wouldn't make sense for us to have an undefined velocity. And if we think about the denominator of this, t squared minus 2t plus 10, we know that the discriminant, right, b squared minus 4ac, that chunk of the quadratic formula that's inside the square root, if we evaluate that, negative 2 squared minus 4 times 1 times 10, we get a number that is clearly less than 0. So we know that the denominator is never equal to 0, right? And we can see that t squared minus 2t plus 10 is always a positive number, right? When you have a quadratic that doesn't have any solutions to it, any roots, right? Doesn't cross through the x-axis, and then it opens up, it's concave up, right? 1t squared, a positive a value. You know that it's always greater than 0. And so then we'll just set 2t minus 2 equal to 0. That's when t is equal to 1. So the only time when this particle might be changing directions is at t equals 1. And so we can make a little sign chart here with 0, 1, and the end of our time interval, which is 8 on it. And note that if I pick something between 1 and 8, like 2, and plug it in here, the numerator, 2t minus 2, is going to be positive, and the denominator is always positive, as we already said. So the velocity is positive, which means that the particle is moving to the right. And from 0 to 1, if you put in something like a half to your numerator here, you're going to get a negative, and then you'll divide by a positive. It tells us our particle is moving to the left from 0 to 1. So we could say v sub p of t is less than 0 for t equals 0 to t equals 1. So it is moving to the left on that interval. And we'll put the 0 in a bracket because that velocity is still negative at 0. But at 1, it's equal to 0, so we'll put that one in a parenthesis. And you got 2 points here, 1 for correctly finding the derivative, and 1 for an answer with your reasoning. Part B here says, find all times during which the two particles travel in the same direction. So we've already noted that particle P is going left on 0 to 1, and it's going to the right on 1 to 8. So we've already got that. Then we just need to worry about particle Q. And particle Q, we're already given its velocity. So v sub q of t, which is t squared minus 8t plus 15, which we can factor into t minus 3, t minus 5, equals 0 when t is 3 and when t is 5. So we'll just make a sign chart here using 0, 3, 5, and 8. And if we test something like 1 into v sub q, or if I test 1, right, t minus 3 is negative and t minus 5 is negative. And if you multiply two negatives together, you get a positive. So the particle is moving to the right. If you test something like 4, between 3 and 5, you get a positive for t minus 3, but a negative here. So a positive times a negative is a negative, and we're moving to the left. And testing something like 6 gives you two positives here on t minus 3 and t minus 5. So we're back moving to the right. So now we just look at our overlaps, right? So from t equals 0 to 1, p is moving left, but on none of that interval is q moving left. It's always moving to the right there. And then q is moving to the right from 0 to 3, which overlaps with 1 to 8 here a little bit, so 1 to 3. So it looks like they're both moving to the right. And we'll just stay in the same direction on 1 to 3. Right? And we'll say, we'll just go with some open intervals there because it's an open interval for the 1 and it's an open interval for the 3 for Q and an open interval on the 1 for P. So the overlap is going to be the open interval. And then we'll look further along, we can't do anything else with the lefts because P is only moving to the right from 1 to 8. And Q is moving to the right again from 5 to 8. So we'll say, and 5 with an open interval because Q was not moving left or right at 5. Its velocity was 0. And then at 8, we can put a bracket there on that one because they both have a bracket there. And they're both moving to the right at t equals 8. So they're both moving in the same direction on 1 to 3 and 5 to 8 because, and we'll say because v sub p of t and v sub q of t have the same sign. And you can indicate that they're both positive if you want, but just saying the same sign is good enough. You got 1 point for the intervals and 1 point for the explanation with like the analysis that you basically did up there on the top. Part C asks us to find the acceleration of particle Q at t equals 2, and then talk about the speed, whether it's increasing or decreasing or neither. So the acceleration of Q at t equals 2, well, A sub Q of 2 is equal to V sub Q prime of 2. Okay? And so we'll note that V sub Q of t is equal to 2t minus, not V sub Q, V sub Q prime of t is equal to 2t minus 8, and that's A sub Q of t. So A sub Q of 2 is just 2 times 2 minus 8, which is -4. Okay? So you're going to get yourself 1 point for that value there. And then the second part of the question is the speed of the particle increasing, decreasing, or neither at t equals 2? And so speed increases. Note that we're talking speed, not velocity. Speed increases when acceleration and velocity have the same sign. Okay? And speed is decreasing when they have opposite signs. So we're going to note that V sub Q of 2, and I don't remember what it was. So if we go back to our chart here, we can look. V sub Q at 2 was positive, right? Between 0 and 3, V sub Q of 2 was positive. And so we're going to say V sub Q of 2 is greater than 0. We don't need an exact value for it. But we can say V sub Q of 2 is greater than 0. And A sub Q of 2 is less than 0. So the speed is decreasing because they are opposite signs. And you want to make sure you write that little bit that says because they are opposite signs. And that will get you another point there for your explanation on why the speed is decreasing. And part D here says find the position of particle Q the first time it changes directions. Well, let's go back to part B again. The first time that particle Q changed directions, it went from right to left at t equals 3. So we'll first note that Q changes directions for the first time at t equals 3. You don't need to show that work again. Just make that note. So at t equals 3. So now we're trying to find the position at 3. Well, we know the position at 0. So we can use a definite integral here and say that the integral from 0 to 3 of v sub q of t dt should tell us the displacement of the particle from 0 to 3. So that should tell us what x sub q of 3 minus x sub q of 0 is. And if we want to find x sub q of 3, we can just take x sub q of 0 and add it over here on the other side of the equal sign. So this is telling us that x sub q of 3, which is what we're looking for, is equal to x sub q of 0 plus the integral from 0 to 3 of v sub q of t dt. And x sub q of 0 is 5, right? It's at a position of 5 at t equals 0. So we have 5 plus the integral from 0 to 3 of v sub q. Well, the integral of v sub q of t squared's integral is t cubed over 3. Minus 8t should go up to minus 8t squared, and you'll divide by 2 to get minus 4t squared. And then plus 15t. And of course, we want to integrate that from 0 to 3. So that gives us 5 plus, and now we'll input 3 into this. So 3 cubed is 27, and 27 divided by 3 is 9. And then 3 squared is 9, and 4 times 9 is 36. And then 15 times 3 is 45. And if I plug in 0 to each of those, right, I get 0 minus 0 plus 0. So I don't really need anything there. I'll write minus 0, but it's not really necessary. And we just do the arithmetic there. 9 minus 36 plus 45 should come out to be 18. So we got 5 plus 18, which is a position of 23. And so for this problem, you ended up getting 3 points. 1 for having the correct antiderivative, 1 for remembering to use the additional condition, and 1 for the final answer. And that is the end here of this motion FRQ number 5 from the 2017 AP Calculus AB exam. All right, this is question number 2 from the 2018 AP Calculus AB exam. And it's a particle motion problem, right? We've got a particle moving along the x-axis with velocity given by that function there for time between t equals 0 and 3.5, and it gives us an initial position that the position is at -5 when t equals 0. So first thing it asks is to find the acceleration of the particle at t equals 3. Well, that's pretty straightforward here. Since this is a calculator question, we want the acceleration. We'll just say v prime of 3, the derivative of the velocity, is a of 3. And then we'll just use our calculator to approximate that value, right? And so we'll just go into our graphing calculator here. And to find the derivative, we'll hit math. And we'll go down to option number 8 in deriv. We'll say d dx. We're going to use x instead of t's in these, of course. I like to hit alpha and the x button next to it if your calculator has that functionality to give you the nice fraction. If yours doesn't, that's fine. Just make sure you put the numerator and the denominator into parentheses themselves. And then we have 10 sine of 0.4 x squared, since we're using x instead of t. And then in the denominator, we've got x squared minus x plus 3. And we want to evaluate this when x is equal to 3. And so we get negative 2.118 when we round. And that is the answer to part A. And it's just worth 1 point. Part B asks us to find the position of the particle at t equals 3. And so we're given the velocity, and we can find the displacement by integrating the velocity. So what we'll do is we'll just say if I wanted to find the displacement between the position I know at t equals 0 and the position at 3, I could just integrate the velocity function from 0 to 3. And we would note that that gives us the position function at 3 minus the position function at 0, right? Because the position function is the integral of the velocity function, which would tell us that if we want the position at 3, we could just add x of 0 over to the other side. X of 3 is just equal to x of 0 plus the integral from 0 to 3 of v of t dt. And of course, we have a calculator here. And so all we have to do is just punch it all into our calculator. We know that x of 0 is -5. So really, we're just looking for -5 plus the integral from 0 to 3 of v of t dt. And we'll punch all of that into our calculator. So we've got -5 plus, and then it's math, and it's option number 9 down here. And we're going to integrate from 0 to 3, just like we said we were going to there. And we type in our function again, 10 sine of 0.4x squared divided by x squared minus x plus 3. Don't forget your dx out at the end there. And you should end up getting -1.760 as our final answer for part B. And that was actually worth 3 points. So 1 point just for having an integral of 0 to 3 of v somewhere. 1 point for using the initial condition, and 1 point for the final answer. For part C, it says to evaluate the integral from 0 to 3.5 of v and the integral from 0 to 3.5 of the absolute value of v. And so, again, this is just going to be a calculator question here. So we're just going to go into our calculator, and we'll do math. And option number 9, again, you can just hit the 9. You don't have to scroll all the way down to it. And we're going to integrate from 0 to 3.5 of our v function. And this is why sometimes it's nice to put the function into the y equals so you don't have to keep typing it over and over again. But since we didn't do that, we'll just keep typing it. It's not so bad to do. Same function every time here. Hopefully I've typed this in correctly. 10 sine of 0.4x squared over x squared minus x plus 3 from 0 to 3.5. That gives us 2.844 when we round. So we'll write that out. The integral from 0 to 3.5 of v of t dt was equal to 2.84. I think it was 844. I guess we should check that. 844. And when we integrate velocity, it gives us displacement. So we'll say this is the displacement of the particle on the time interval from 0 to 3.5. And that'd be our explanation for it. And then we'll do the same thing with our integral from 0 to 3.5 of the absolute value of v of t dt. It's going to equal something. Now, before I even find that out, what does that equal? Well, the integral of the absolute value of velocity is an integral of speed. And the integral of speed tells you the total distance traveled by the particle on the interval from 0 to 3.5. And so that's the difference between the two, right? One is the displacement. The integral of velocity is the displacement, and the integral of the speed, or the absolute value of velocity, is the total distance traveled. So now we do need to find that value. So we'll do math, and we'll do option 9 again. And we're once again going to do 0 to 3.5. This time we need an absolute value. So we're going to hit math. We're going to go to the second column, number, choose option 1 for absolute value. And now inside of the absolute value, we'll just put our function 10 times the sine of 0.4x squared divided by x squared minus x plus 3 dx. We'll hit enter, and it will give us 3.737 when we round, so we'll just throw that in here. 3.737, and that is our final answer for part C. We got 1 point for having the 2 correct values here. So that's 1 point. And then we got 1 point for the explanation of each one. In part D, we've got a second particle that's moving along the x-axis with its position equal to t squared minus t. We want to know at what time t are the two particles moving with the same velocity. So we already have a velocity function for the first function, right? 10 sine 0.4 t squared over t squared minus t plus 3. We need the velocity here. So v sub 2 of t is x sub 2 prime of t, which will be 2t minus 1. So really, all we want to know here is when does v of t, or 10, and you can just write v of t if you want, but I'm going to write it all the way out, 10 sine of 0.4 t squared over t squared minus t plus 3, when does it equal 2t minus 1? And so that's easy enough to find out, again, with our calculator. So we'll just go to our graphing calculator, and we are going to graph each of those two functions and look for where they intersect. You can also subtract one function over to the other side and look for the x-intercept, but easy enough to just go in here and graph them each separately. We'll do that. Since most of the other ones, I normally find the 0. We'll find the intersection point this time. So we've got the first function, which was 10 sine 0.4x squared divided by x squared minus x plus 3, and our other function, which is 2x minus 1. We'll just hit graph and see if we can see where they intersect. Looks like they intersected once there. And so we'll just hit second, trace. We're going to pick option number 5 this time for intersect to look for where the two functions intersect. You just kind of want to be on the first curve somewhere near where they intersect, maybe to the left of it. Then on the other curve, just kind of scroll over to the right of where they intersect. And then hit enter there, and then hit enter a third time, and it will tell you that it looks like it's at 1.57054 down there on the left. So 1.571. You don't need to show any other work other than just saying that's at t equals 1.571 and call it good. We got 2 points here for this part, 1 for setting them equal and 1 for successfully finding that value using our calculator. And that is the end here of question number 2 on this motion FRQ from the 2018 exam. All right, this is question number 2 from the 2019 AP Calculus AB exam, and it's a motion problem, and they've given us a chart here telling us the velocity of a particle p moving along the x-axis. We're told that v sub p is a differentiable function, and that v is measured in meters per hour, t in hours, and we know that the particle is at the origin at t equals 0. And so the first question it asks us here is to justify why there must be at least one time t for 0.3 to 2.8 where the acceleration or the derivative of v is equal to 0. And so usually when they ask you about why does the derivative have to equal a specific number, what they want you to look for is the mean value theorem. And so we'll note that the mean value theorem requires a function to be continuous and differentiable. And so we will say v sub p is differentiable, and therefore continuous on the interval that we're talking about here, which is from 0.3 to 2.8. So we want to make sure we make that statement, right? Because the mean value theorem doesn't work if the function is not continuous and differentiable, and it tells us it's differentiable. So differentiability implies continuity. And then we just need to then find the average rate of change of the function, the average rate of change of its velocity on this interval, and see if it equals 0. If it equals 0, then the mean value theorem applies. So we'll say that v of 2.8 minus v of 0.3 divided by 2.8 minus 0.3 is equal to 55 minus 55 over, well, 2.8 minus 0.3 is 2.5. And of course, that equals 0. So by the mean value theorem, and you want to make sure you state the mean value theorem. So by the mean value theorem, v sub p prime of t equals 0 somewhere on the interval from 0.3 to 2.8. And that will get you both points. So 1 point was for showing that this was equal to 0, and 1 point was for the justification using mean value theorem, so saying mean value theorem, and with the statement about differentiability and continuity. Part B here is asking us to use a trapezoidal sum with the 3 subintervals from 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8 to approximate the value of the integral of v sub p of t from 0 to 2.8. So we just need to set up a trapezoidal sum here. The first height of the trapezoid is the width from 0 to 0.3, so that's 0.3. And then we're going to multiply that by 55 plus 0 divided by 2, right? That's our 2 velocities on the first interval there. And then we'll do the next interval. 1.7 minus 0.3 is 1.4. So it'll be 1.4 times 55 plus negative 29, or 55 minus 29, over 2. And then we'll do one more here, right? From 2.8 to 1.7 is 1.1. So it'll be 1.1. And then it'll be, well, negative 29 plus 55, again, divided by 2. And so we just need to go ahead and evaluate that. I'm not going to go through the effort of punching it into my calculator, because I think we can all do that. It's equal to 40.75. And they just gave you 1 point there. You need to get the right answer, and you need to show a setup there using a trapezoidal sum. So 1 point for that. Part C says that we have a second particle, Q, moving along the x-axis, and its velocity between 0 and 4 is given by this function, 45 root t cosine of 0.063 t squared in meters per hour. And we want to find the time interval during which the velocity of the particle is at least 60. So, in other words, we need to see when that velocity function equals 60 and then check when the function is greater than that. And then we want to find the total distance traveled by the particle during the interval on which its velocity is at least 60. So first thing we'll do is we'll just set v sub q of t equal to 60, and we'll graph it on our graphing calculator. We can either do v sub q of t, graph that, and graph y equals 60, or we can graph v sub q minus 60, and then see when that has x-intercepts. So that's what I'm going to do, is I'm going to graph v sub q minus 60. You don't necessarily need to write that as you do it. So I'm going to go to my graphing calculator here, and we'll go into our y equals, and v sub q of t was 45 times the square root of t, so we'll use x, and then times the cosine of 0.063 x squared, and that's what we want to graph, minus 60, and we're talking about on the interval from 0 to 4. So before I graph it, I'm just going to click window, and then I'm going to go down to xmin, or start on xmin and put it as 0, and xmax as 4, and now I'm going to hit graph, and I can see that my velocities there, minus 60, are equal to 0 in a couple places on this interval. So we need to find those places, so we'll hit second trace. Option 2 is 0. And we'll scroll to the left, so we're the left of the first x-intercept, and hit enter. And then we'll scroll to the right and hit enter. And then we'll hit enter again, and it gives us 1.8661815. So we will write that down. We'll call it at t equals, we'll call it a. I like to assign a little variable for these so I don't have to keep writing it over and over again. And that was 1.8661815. 0.661815. And then we'll find the other one, which we're going to call t equals b. So we'll go back to our graph here. We'll hit second trace again, choose option 2 for 0, and scroll over till we're kind of close to that other x-intercept, which might take a little bit of time here, but that's okay. Good enough, hit enter. Now it says right bound. We move to the right, hit enter. It says guess, hit enter. And you get 3.5191744. So we'll put that down. That was 3.5191744. And so we found these two places. So it asks us the time interval. So we're going to say v sub q of t is greater than, and let's see, it asks for when is it at least 60. So we'll say greater than or equal to 60. And so then now we're going to include those endpoints there. So we'll say on the interval from A to B. And of course, you can write out the numbers if you want, but since we've defined them as A and B, it's perfectly okay to write A to B, just like that. So that is worth 1 point, just finding that interval. And then the second thing it asks for is to find the total distance traveled by the particle during the interval on which the velocity is at least 60 meters per hour. Well, we know then that what we need to do is an integral from A to B of our speed function, which is the absolute value of v sub q of t. Now, we could get away with not doing the absolute value here because we know that the velocity was greater than 60 on this interval, which means the velocity was never negative on this interval. But just good practice to put it in the absolute value just in case you're misinterpreting something, because the absolute value, the integral of the absolute value of velocity is always what you need to do to get your speed or your total distance traveled. And so we'll just do that on our calculator. So we will go back to our graphing calculator. We're going to quit out of that, second quit. We're going to hit math, and we're going to go down to option number 9, FNINT, which gives us an integral. And our lower limit was 1.8661815, and our upper limit was 3.5191744. And our function, conveniently, we already had it graphed as y1 in our y equals menu, or actually we didn't. We had the function minus 60. So we should really go back and don't use y1 like we've done some other times because we had the function minus 60. So we'll hit math and go to the second column for absolute value first, and then we'll just put our function in, which was 45 square root x, and then it was cosine of 0.063 x squared. We'll close our parenthesis there, and we will put a dx outside of there, and we should get our answer of 106.108754, or 106.109. So 106.109, and always put your units, which is meters, since it's a total distance traveled. Even though it didn't say to indicate it, it's always a good habit to be in. And there we go. That's the end of part C. We got 3 points for that. So 1 for the interval, 1 for the integral itself, and 1 for the final answer. In part D here, our last part of this question, it says at time t equals 0, particle Q is at x equals negative 90. And then it wants us to use the result that we had from part B and the function v sub q from part C to approximate the distance between the particles P and Q at 2.8. Well, we'd already found that the first particle, right, particle particle P. P is at 40.75 because we had read earlier that its initial position was 0, and we approximated its displacement there to be 40.75. So we've already got particle P. We just need to find the position of particle Q at 2.8. So to find the displacement from 0 to 2.8, right, of v sub q of t, that would give us the position of q at 2.8 minus the position of q at 0. Or in other words, in order to find the position at 2.8 of q, we need to do the position at 0, which was just told to us to be negative 90, plus the integral from 0 to 2.8 of v sub q of t dt. And so we'll just go into our graphing calculator, and we will do negative 90 plus math, option number 9, the integral, and we're doing it from 0 to 2.8. And of course, it is of the same function that we've used a bunch of times here. It's 45 square root of x, and then it is cosine of 0.063 x squared. We'll close our parentheses there, and we'll go off, put our dx, and we should get a value of 45.937653. Not 973, 937. 937653. And of course, the question says approximate the distance between the two particles. So we'll just then go ahead and do 45. I said 45. Maybe I should write 45 here. 45.937653 minus the 40.75, which of course we can just do right here. Minus 40.75 gives us 5.188 when we round. 5.188 meters apart. And the point breakdown here for part D, they gave you 3 points for it. One was just for doing this integral of v sub q of t at all from 0 to 2.8. One was for using this initial position, and then the last one was for the final answer. And that is the end of this FRQ number 2 from the 2019 AP Calc AB exam.